In the previous semester, we were dealing with analog signals, and there are certain problems associated with the analog signals, which we will discuss as we go to the digital signals, and due to which we require to change the analog signals to digital signals. And for that, we require sampling of the signal. And in this lecture, we are going to start with the sampling theorem and what are the requirements of it and how it applies to different signals we are going to discuss here. The sampling theorem, the statement of sampling theorem can be given in two parts. First one is that a band limited signal with the maximum frequency component FM Hertz is completely described by its sample values at certain uniform intervals less than or equal to 1 divided by 2 FM second apart. So what that means is that suppose we have a band limited signal. When I'm saying band limited signal means it is limited by the frequency and it has a maximum frequency component FM, means the maximum frequency in that signal is equals to FM. And we want to describe that signal with the help of different sample values taken at uniform intervals less than or equal to 1 divided by 2 FM. So if we want to describe this signal and that it has a frequency FM, then we need to plot or we need to define it at uniform intervals which are less than or equal to 1 divided by 2 FM second apart. The second statement is a band limited signal with maximum frequency component FM Hertz may be completely recovered. Now we have we defined it, or we can say that we are taking the samples to create the signal in the first part. But now in the second part, if we want to recover a signal from the sample defined, then may be completely recovered from the knowledge of its sample taken at the rate of 2 FM. Here we were talking about time intervals. Here we are taking 2 FM samples per second or more. Means if my sample rate is greater than or equals to 2 FM, then we will be able to recover the signal from the samples. Else we will not be able to. The first part represents the representation of the signal in its samples and minimum sampling rate required to represent a continuous time signal into its samples. It is continuous time signal. The second part of the theorem represents a reconstruction of original signal from its samples. Combining the two parts, the sampling theorem may be stated as under: a continuous time signal may be completely represented in its samples and recovered back if the sampling frequency is Fs greater than equals to twice Fm. Here Fs is the sampling frequency and Fm is the maximum frequency present in the signal. So basically what it means is that frequency, if you know that frequency is the appearance of the signal. So if my sampling frequency Fs is greater than or equals to twice of maximum frequency component present in the samples, then we can recover back the original signal. Now, proof of a sampling theorem, and to make you understand what basically samples means. So we have a continuous time signals like this, and we are taking some uniform intervals of time. So basically, just consider it that way, that this is 0, this is 5, and this is 10. So if I want to divide my signal with respect to time instants, so let's say I'm saying 0, then this time instant is 1, that's 2, that's 3, that's 4, this is 5, then 6, 7, 8, 9, 10. So what we are doing is we are changing a continuous time signal into a discrete time signal. Why it's a discrete time signal? that it will be defined at 0, 1, 2, 3, 4, 5, means discrete times. And this discrete time is constant. So you can see this gap between them is 1 hair, this 1 hair again, and so on. It can be 2 or 4, depends upon what you want to do with the signal. So suppose that we sample the signal xt instantaneously and at uniform rate once every ts seconds. So this is our sampling time, or you can say the difference between two samples. This ts is basically equals to 1 in this case. So we can say the sampling period is equals to ts. So now we are generalizing it. Earlier I explained you with respect to 1, 2, 3, 4. So the sampling period if is equals to ts, and the sampling frequency, we know that frequency is inversely proportional to time. So fs will be equals to 1 divided by ts. Also called sampling rate, or you can say it's number of samples per second. So if we have a continuous time signal xt and the Fourier transform, if we change, we can say use some other signal xgt, and we denote it as xn into ts. Sorry, it's not Fourier transform. We are representing it by another signal y. This is your xt and this is your gt. Means this is your continuous time signal and this is your discrete time signal, which is basically equals to x into n into ts. Okay, now Nyquist rate, and sorry, it's Nyquist interval. So it's QUIST. So what happens is that when the sampling rate becomes exactly equals to 2 FM samples per second, then it is called Nyquist rate. So if your sampling frequency is equals to twice FM, so this thing has been discovered by someone named as Nyquist. So it came as Nyquist rate. So Fs is equals to twice of Fm. Nyquist rate is also called the minimum sampling rate or critical sampling rate. So if your sampling frequency is not equals to 2 FM or greater than that, then you will not be able to recover a signal from its samples. So basically what it means is that if this is given to you and your Fs is not greater than or equals to Fm, twice of Fm. What is Fm? Fm is the maximum frequency component in this signal. So your sampling rate for this signal in order to recover must be greater than or equals to the frequency of this signal, twice of frequency of this signal. And it is called as minimum sampling rate or critical sampling rate. Similarly, maximum sampling interval is called the Nyquist interval, and it is equals to, if this is frequency, then time becomes 1 divided by 2 FM seconds. Sorry. Now, if we have a signal GT and we are using it like from minus infinite to infinite, we can say it's xt into delta t minus ns. So if you remember this function, this is your delta function, which we did in signals and systems. So what will happen is that if I put t minus nts equals to 0, then it will be equals to x and ts. And whatever the value of your n will be, gt will be defined at that point only. So suppose n is equals to 1, then you will get g1 value corresponding to this signal. Okay, this is the way of representing that x of nts with the help of delta function. Again, it's written same. The only difference is that they put t, replace the t by nts. So we can write it. If you remember, we did it in Fourier transform when we were finding the integration. Now, if we use Fourier transform pair, so if we say that GF is the Fourier transform pair of it, then we can say that whatever the Fourier transform of this will be, if you remember the Fourier transform, then I'm just taking this one as GT and I'm representing the Fourier transform of it as equals to x of f, then you can say that Fourier transform of this will be xf. So if two signals in time domain are multiplied together, then in frequency domain they will be convoluted with each other. Sorry. And the Fourier transform of this will be xf, capital XF, x changed to capital F, sorry, capital X. Now with respect to this, because now we are changing it into the different variable. If you remember the convolution problems, then it will remain same as delta, and t will change to f, ts will change to fs, because we are taking now from time to frequency, and n is changed to a different variable in frequency domain, which is again in the same range, minus infinite to infinite. And the relation between n and f are contained in this fs. Now if we multiply these two signals and we take a convolution of these two signals, we can just say that x will come here. If you remember the convolution of x or any function x with delta function, then it will be x f minus mfs, okay, which is equals to gf. This has been shown here, how it changes to frequency in this t minus I naught as given to you. If you take a Fourier transform of this, then how it's going to change it. So this is your frequency fs. Here the time is t naught, where it is ts here. So it will change to 1 divided by t naught, 1 divided by t naught, and this will be f minus n divided by t naught. So if you see that 1 divided by t naught is equals to fs in this case. So we can say where xf is the Fourier transform of the original signal xt, and fs is equals to twice fm equals to 1 divided by ts. Now the Fourier transform of delta function is, any delta function is e raised to the power whatever the value there is. And ideally the Fourier transform of delta t is equals to 1, but we have a time shifting here, so we are applying a time shifting property and then we are finding it. So whatever the value of n and ts is, that will go there, e raised to the power minus j omega nt, if you remember that with respect to that. So Fourier transform of delta t minus nts will be this. Then putting this in equation 1, we can say that gf will be equals to summation x and ts, means we are putting it here, and will be equals to x and ts exponential minus j 2 pi n f ts. So this relation is called discrete time Fourier transform here. And gf is equals to minus infinite to infinite summation xn divided by 2fm. Why? Ts is equals to ts. If we need to find the value of ts, exchange them. So it will be ts will be equals to 1 divided by 2fm. It will be n divided by 2fm exponential of this. Put the value of ts also here. So we can say that from equation 2, this one is equals to gf will be equals to fs into xf plus fs into summation of this, where m should not be equals to 0. What has been done here is that the m equals to 0 has been taken out here. So when m equals to 0, it's from minus infinite to infinite. When m equals to 0, then it will be xf into fs. So that is, this one is fs into xf. And then minus infinite to infinite is represented here, but it's mentioned here that m is not equals to 0. Now suppose that xt is strictly band limited with no frequency component higher than fm. Means my xt will be band limited to FM. If I change it to XF, then the plot will be something like this. So it's from minus FM to FM. So XF is equals to 0 for all frequencies greater than equals to FM on the negative side also. So then from equation 4, we have GF will be equals to Fs into XF. This part will become 0. Why? Because it's between this range only. For all these frequency component, this part is not going to exist. So GF will be equals to this. XF then will be equals to, if I find the value of XF, will be GF divided by Fs. What is Fs? Twice FM. So we can say X of F equals to GF divided by 2FM in this range. Now from equation 5 and equation 3, this one, we can find out that XF means just put the value of GF here. XF will be equals to this. Therefore, if the samples values xn divided by 2fm of a signal xt are specified for all n, then the Fourier transform xf is uniquely determined by using discrete time Fourier transform of equation 6. So xt will be equals to minus infinite to infinite x of x f exponential e raised to the power j 2 pi ft df. So we are taking now inverse Fourier transform here to find the value of xt. Put this value here, and if you change the order of summation and integration, so this part will come inside and this part will come outside. So summation will be here, so it will be x and 2fm will come here because n is in here, and then it is 1 divided by 2fm minus fm to fm exponential. In these two, you can take whatever that is common, so it's j2 pi f t minus n divided by 2fm will be there. Now integrate it and put the limits minus fm to fm, and you will get this. Now sine n pi, so 2 pi fm t minus n pi divided by 2 fm t minus n pi. If you remember, this is equals to a sinc function where the angle and the denominator are same. Then we can write it as sinc 2 pi fmt. So it's pi is missing here, or you can cancel the pi here if you want to cancel this, cancel with this. So you can take sine outside. Sorry, pi is missing, so it will be sinc pi must be here. Or you can represent it directly like this using the pi here. So it's up to you. So equation 7 provide an interpolation formula for reconstructing the original signal xt from the sequence. It's a CONS here. The original signal from the sequence of samples values taken at this, with the sinc function playing the role of interpolation function. Okay, so if we have this from equation, we can have GF equals to twice FM into XF, and your GF then will be of this form, repeating after every FS frequency component. So the spectrum of the sampled version of XT for a sampling frequency rate Fs equals to 2fm. When a continuous time band limited signal is sampled at a rate lower than Nyquist rate, that is Fs is less than 2fm, then we call it undersampling or undersampled signal, and it leads to a problem of aliasing. So what is aliasing here is, if you see that this signal, suppose I start with this signal is ending here, but before this starts, the signal ends here, or the plot ends here, another plot start from this side. So this portion is repeated again. This is called aliasing. So aliasing refers to the phenomenon in which a high frequency component in the frequency spectrum takes the identity of a low frequency component. So basically you can say this is high frequency component, this is low frequency component. They both are here. So the high frequency component in which a high frequency component in the frequency spectrum takes the identity of a low frequency component in the spectrum of the sample signal. Because of this overlap, due to aliasing phenomenon, it is not possible to recover original signal from the sample signal. To avoid aliasing, we may use two corrective measures. Prior to sampling, a low-pass anti-aliasing filter is used to attenuate those high-frequency components of the signal that are or not essential to the information being conveyed by the signal. Second is, the filtered signal is sampled at a rate slightly higher than the Nyquist rate. And this is more convenient way that you always sample the signal at a rate slightly higher than the Nyquist rate. So if Fs is greater than 2 FM, then the signals will be like this, and there is no overlapping, then you can easily recover any frequency component. Now, what is reconstruction filter in this? The reconstruction filter is a low pass filter with a pass band extended from -FM to FM. So you want to reconstruct, means take the signal out of it. The filter has a transition band extended for positive frequencies from FM to Fs minus FM. Means you can extend it to right hand side, or you can extend it to the left hand side. So this is what a reconstruction filter is. This is just to explain you, otherwise we are not going to use it.